Hello there, Year 12s. I'm here to do a bit of a summary on the projectile motion topic. So we're going to run through how to solve problems in this topic and the main points of what needs to be known for the exam and for tests and the like. So first of all, with projectile motion, a thing that you need to understand is that the horizontal and vertical components of motion, we treat them independently of each other. The reason for that is if you look at any object that's being thrown or projected frame by frame, so like this stop your motion diagram here, we see that horizontally the same distance has been traveled from left to right with each frame, so it's always going about this far forward with each frame. And if the distance traveled horizontally is the same, then that means it's traveling horizontally with a constant velocity. So horizontally we know that the velocity must be constant. Whereas vertically, if we look at the vertical distance traveled, it's traveled up a little bit there. And then in the next frame, it's traveled up a bit more, but not as much. And then not very much vertically again, and then the distance traveled actually changes direction, so it gets displaced downwards now, and the displacement is increasing with each frame as it goes down. So vertically we know that with each frame it's doing a different displacement, so we know that that means that the vertical velocity must be also changing to cover those different displacements. And that's because there's an acceleration going downwards that is constant in size and direction. And these two factors, the fact that you've got a component of the velocity that is constant and another component that's got a constant change applied to it, they result in parabolic paths and projectile motion that we observe. Question you might be asked would be to draw vectors that represent different components of the velocity on a stop motion diagram like this one. So if you're drawing, say, horizontal components, the horizontal component of the velocity is always going to be constant. So we could draw arrows like, draw arrows like this to represent the horizontal velocity, as long as they're the same size and direction, because the horizontal velocity is always the same. And typically we draw them going from left to the right. We could also talk about a different one, like say here, all these vectors represent the vertical velocity at those different points. So here we can see the vertical velocity, v subs v for vertical velocity, starts off going upwards, and that's going upwards by not as much because there's acceleration downwards. Eventually it'll reach 0, so I just forgot that little one there. Eventually it'll be reaching 0, and then it turns around and goes in the negative direction as well. You could also be asked to draw vectors to represent acceleration. Go there, some vectors representing the acceleration. The acceleration is always the same and it's always going down. So we should have vectors that are the same size, pointing in the same direction to represent acceleration is down. They could also represent force vectors for the gravitational force on the object. It's always the same, it's the weight, it goes down, always the same everywhere. One last thing, we can also draw vectors to just represent the velocity at any point in time. So if we're just talking about velocity, not any component of the velocity, horizontal or vertical, then we're talking about the overall velocity, the net velocity, the total velocity at each point, which means that the horizontal and vertical components are added together and the velocity is actually going in the direction that the projectile will be going at any of those points in time. It should be a tangent to the direction of the path. So it starts off like this, and then eventually it gets to a stage where it's purely just going from left to right, where the vertical component reaches 0, and then when the vertical component starts heading downwards, we get the total velocity with an angle starting to go downwards as well, but it's always got that horizontal component making it go from left to right. Let's move on in talking about the two vector components here. So over here in this diagram, we've got that the velocity at any point can be broken up into a horizontal component and a vertical component. We can find what those components are by using these two formulas. So we can use v cosine theta to find the horizontal component, or we can use v sine theta to find the vertical component. Whenever you're solving a projectile motion problem, it's very important that the total velocity is broken into these components, because we solve problems and use equations with those components independently. We don't do it with the total velocity at any time. We never do that in projectile motion. We always break them up into components and work with the components. So just talking about those two components, we've got the horizontal velocity. You need to know this is always constant, because there is no acceleration horizontally. Gravity does not act sideways. And that means if one is solving a problem and you're working with the horizontal direction, pretty much all we can use the horizontal direction to do is relate the horizontal velocity to the range and the time of flight. Because there's no acceleration going horizontally, we basically just use the relationship speed is distance over time, which is usually written in this form in Year 12 for finding the range. So the horizontal range, distance, is equal to speed times by time, with the speed being the horizontal velocity in this case, and the time is just time of flight. So typically we use this component if we want to find how far is the projectile going horizontally. We could also use it to find time of flight though as well. If we actually know what the range is and the horizontal velocity as well, we can basically just use this relationship to find anything in that direction, which is very good and very handy and very simple. While we're on the topic of the horizontal velocity, and this formula on calculating range, we can move on to what results in maximum range by talking about this here. So to maximize range is calculated by distance equals speed times by time, and you're expected to know that from ground level the angle that results in maximum range is 45 degrees there. The reason why this is because 45 degrees provides a nice balance between the horizontal and vertical components of the velocity. So I've just drawn this vector triangle up here. So if you have 45 degrees there, you actually get horizontal and vertical components that are the same size. And that's important because to calculate range, we do horizontal velocity times by the time, so both of those factors are important. So we need plenty of horizontal velocity, and we also need plenty of time. 45 degrees just gives a nice balance between the two, because we've got a greater vertical component, and the vertical component of the velocity contributes towards time in the air. So if this component here is greater, then we're in the air for longer, but we also sacrifice this component. And if this component is shorter, well, we can make the horizontal velocity larger, but then we sacrifice time in the air. So essentially, we're getting enough time in the air and enough horizontal velocity to cover the distance, and the balance results in us getting maximum range. But this changes if we go from a greater launch height. So if I go down to here, if we're at a greater launch height, we actually need a lower angle than 45 degrees to get the maximum range possible. The reason why we need a lower angle is because if we lower the angle from 45 degrees, we actually increase the horizontal component of the velocity. So in this vector diagram here, if this is smaller than 45 degrees, well, if we have the same starting velocity, you can picture taking that arrow and kind of rotating it so it goes a bit further downwards. So more of it is going in the horizontal direction, so your horizontal velocity gets larger. And we can do that because we've already got more time of flight from the fact that we're launching from higher up, so we get more time in the air. So we can sacrifice the vertical velocity because we've already got more time in the air due to being from a greater height. So we can spend more of our velocity on the horizontal velocity to give us greater range from that. So I'll scroll back up to here, where you can actually use v sine theta to find the vertical component of the velocity, and the vertical component of velocity is used in lots of problems because it's the more complicated one. Because in the vertical direction, we know that the vertical velocity changes because we have acceleration that acts vertically. It acts vertically downwards at minus 9.8 all the time. Different problems you could get in the vertical direction, let me rephrase, different problems that you could get that involve using the vertical direction could be a horizontal projection, where you've got something that's just going left to right, starting off with a velocity that's entirely horizontal. So if you have a case like this, you need to know that the velocity in the vertical direction is equal to 0 to start off with, because we've just got an entirely horizontal velocity to begin with. So we can actually, in the vertical direction, use v0 equals 0 as our starting vertical velocity, because there's no going up or down here to begin with. So that's quite useful because we can use this equation here to find a velocity at a later time. We just essentially have to go a times by t. What we can also do is find the time it takes to fall for a certain distance by using this formula here, because that first term disappears and we end up just using this to find how far does it fall in such a time. Or if we already know how far it's falling, we can actually rearrange this to find the time of flight. We could also use this formula here to find a displacement or a velocity if we don't actually know what the time is. Because there's no time in this equation, but that's okay, we could use it to find a final velocity or a displacement if time is unknown. If we keep going down, you might also see problems that look like this, where something's being projected at an angle, and this is probably a bit more common. Before you do anything, you should break that total velocity into a horizontal component and a vertical component. You can use the horizontal component to find range, like I've talked about before. The vertical component, though, we use to mainly find the time of flight. To do that with this case, we use the trick where we know that halfway through, the vertical velocity is equal to 0 at the maximum height. So we can find the time of flight by using this equation here, with that first term there being 0, and rearrange it to find the time, and that's the time taken to get up to its maximum height, and then we just double it to find the total time because it's a symmetrical situation. A lot of problems also look at finding the maximum height, and we can use this equation here if we know the time, because that's already arranged to find a displacement, or we could use this one here and rearrange for s if we don't actually know what the time is yet. Finally, we could get problems where we're asked to find a velocity at a particular point in time. So not just a component of the velocity, a total velocity. So to do that, we need to recombine the two components. To do that, we need to know what they are. VH is usually known because it's always constant, whereas the vertical component, we need to find what that is, and we can usually just use v equals v0 plus at to find the velocity vertically at that particular time. Then to find the total velocity, we draw a vector diagram by adding the two components together to get the hypotenuse, which will be the total velocity at a particular angle, which could be going up or going down depending on what the vertical velocity is doing, whether it's positive or negative, going up or going down. Then to find that total velocity, we use Pythagoras to find it, because that's a right angle triangle. You can use Pythagoras. To find the direction there, we just use trigonometry, and if we use the tan rule, we can relate the opposite to the adjacent side, which is always vertical over horizontal components there. And the angle is usually given in reference to the horizontal direction. So this could be below horizontal by a certain amount of degrees, and this could be above. And I'll finish up there for the next video because I'm at